Greetings. My name is
Hello.
Dr. Bradley Wolf. Greetings again. I'm Dr. Bradley Wolf, the program chairman of the 28th annual ISHRS meeting that takes place in about a week. And today we're going to be talking to one of our featured speakers, Alexey Terskikh, who's joining us to talk about the regenerative medicine approach to hair restoration. Dr. Terskikh is an associate professor of neuroscience, developmental biology, and aging program at Sanford-Burnham Medical Research Institute in La Jolla, California, where he's an assistant professor. He earned his Ph.D. at the University of Lausanne in Switzerland and received his postdoctoral training with Professor Irving Weissman at Stanford University. To the right, you can see the comments area. If you would like to, you can submit questions. If we have time at the end, we will address them. So, Dr. Terskikh, thanks for joining us. How are you?
Thank you. Great to be here. I've been tenured actually several years ago, so I'm an associate, which always helps to keep the position. But everything else is great. Yeah, thank you.
Good. Well, we have some questions. I'm going to get right into the questions. Prior to working with the hair follicle, you were studying molecular mechanisms of neurogenesis and the neuropathy and treatment of the Zika virus infection. How did you go from that to studying hair follicles?
Yeah, thank you. That's an interesting question indeed. We've been studying for many years mechanisms of neurogenesis, including the questions of how embryonic stem cells differentiate into neural lineages and how neuroepithelial cells make neurons. And in the process of that study, we discovered a way to make a neural crest in the dish. And not any neural crest, but a particular type of neural crest, which is called cranial crest. And there are several events that were at that junction happening. One important event was, my father, who is a developmental biology professor in Moscow, now retired, but at that time, has been started complaining a little bit to me that I didn't talk to him often enough. And so, when your folks start to complain, you need to do something about it. And so we decided maybe we start a project together. So I went to Moscow and we selected a student. And then we thought, what can we do? And at that time, the second event was that several laboratories, including Lucas Sommer and Hideki Akano, published some couple of exciting papers suggesting that hair follicles in the craniofacial area, including whiskers in mice, and then mustache and beard in humans, these hair follicles are maintained by the dermal papilla cells that originate from neural crest and not from mesenchyme. Mm-hmm. So the rest of your body are covered with the hair follicles where dermal papilla are coming from mesenchyme. But the whiskers and the mustache are from neural crest. And so we thought, because we just published this work on a neural crest differentiation, that we can use that strategy and obtain dermal papilla via the neural crest intermediate. And still the best way, actually, to my knowledge, to generate dermal papilla. And so, we got a student in common, and then long story short, that was a very successful project. And we demonstrated a few years ago that indeed, neural crest is a great source of the dermal papilla cells that are folliculogenic.
Well, that was my next question. I guess you partially answered it. How do neural crest cells figure into the equation to reproduce dermal papilla cells?
Right. So that's, I guess, the two questions is wonderfully dovetails to each other. So there is in the most part of your body, the hair follicles are maintained by dermal papilla cells that they're coming from mesenchyme. And in a few areas, that is has a different mechanism, so neural crest. For whatever reason, so it's a wonderful developmental questions why there would be neural crest, but there's a lot of tissue in a craniofacial area that contributed virtually entirely by neural crest. Some trachea, for example, cartilage in the nasal cartilage our teeth and salt and pepper. It's a half mesenchyme, half neural crest. The lower jaw is in particular almost entirely from neural crest. So a lot of tissue contributing in a year, and a lot of different tissue, outflow tract and a heart. So it's an interesting congregation of cells. Now, although the origin of the cells, developmental origin, is different, their appearance and mechanistic properties are exactly the same. You actually won't be telling difference between the cells of different origin. They're exactly the same. So, so very interesting. We were fascinated with the neural crest, which called sometimes the fourth germ layer. Hopefully that will answer
that is interesting.
that question.
Yeah,
I should say also that
I actually had no idea that. And is that something that you figured out, or was that common knowledge prior to that? Or did you actually figure that out?
The two laboratories published, and that will be during the talk. I'll show these beautiful images from Lucas Sommer and Heiduki Okano. By using Wnt1 Cree, the zilliter mouse, they showed that they can trace the cells all the way from the fetal position in the neural crest to the hair follicles in the whiskers. And that hair follicles and whiskers has a beautiful area highlighted of dermal papilla that gives the origin. They have a lineage tracing essentially. And interestingly enough, neural crests also give rise to melanocytes that gives the color to the hair. In fact, neural crests give rise also to peripheral nervous system that innervate the bulge area of the hair follicles, as well as some of the smooth muscle in the periphery that also present in the hair follicle. So it's a very interesting relationship between the neural crest derivatives and the hair follicle.
Yeah, Alexey, you're breaking up a little bit. I don't know if your connection's okay, but it's kind of going in and out at time.
Let me see.
But we'll just keep going.
I think I'm connected. The connection here is pretty stable.
Yeah.
Let me know if I need to repeat something.
Okay, we'll just continue. Can you comment on the oncogenic potential and abnormal aging properties of induced pluripotent stem cells? There has been talk that they could cause cancer and that they go through limited number of cycles. I don't know what your experience has been, or if you can enlighten us on those two possibilities.
Absolutely. So what we'll know, Shinya Yamanaka was awarded the discovery, Nobel Prize for discovery on induced pluripotent stem cells. And I think this is the only type of stem cells and that I know which actually could be maintained and amplified. I would not say indefinitely, but for a long time. I mean, several dozen passages, definitely not the limit. In fact, in early days, there's been a study comparing, I believe, those cells amplify until to 90 or 100 passages, and they were reasonably pluripotent and give rise to virtually the same type of cells. Now, as everything in vitro, you might encounter some accumulation of mutations, but if the conditions are proper and the colonies are healthy, I believe this is pretty much the best model. If you can amplify something in vitro, that'll be induced pluripotent stem cells. So, so I think I'm not worried about the aging phenotype. In fact, it's been demonstrated very elegantly by different investigators, including Rusty Gage across the road, that when you convert adult somatic cells to the induced pluripotent fate, that process itself rejuvenates the cells dramatically. This is one of the, and there's a different strategies now, adopted the different labs where they try to overexpress, for example, Yamanaka factors transiently in the mouse and in attempt to rejuvenate the tissue and organs. Now, it's clear that because cells are pluripotent, they also endowed with this capacity to proliferate. And if that goes out of control, that's called a tumor. And the Minerva report, and then it's known in the mouse field that when we transplant embryonic stem cells or embryonic carcinoma, they proliferate and form teratomas. Now, I'm less concerned in humans. Frankly, in fact, it's not easy to make teratoma or cancer out of iPSC. It's a very delicate balance that will differentiate pretty much under any condition, except if the conditions are perfectly fitted for the self-renewing capacity. So the real danger that one can think of is when we transplant proliferating descendants of iPSC, the progenitors or transiently amplifying progenitor for some kind of lineages, and these progenitors are unable to differentiate properly in the environment and get locked into that, proliferating cycle, which is a characteristic of most tumors. The cancer is not, arising from stem cells, as Irving Weissman and others elegantly demonstrated. The cancer is usually arise from this transiently amplifying proliferating progenitors that enable, as a block in continuing differentiation. But with respect to what we're doing, I don't think this is a real kind of danger question. And again, the reason being, when we're talking about bona fide stem cells in the tissue, then these cells can actually only be maintained within a particular niche. It's a delicate niche, and it has to have all the signaling pathways engaged. Now, in the absence of these pathways, and normal stem cells will just differentiate. I'll give rise to progenitor. The progenitor will differentiate to the terminal differentiated cell in a skin. That will be keratinocytes, and these cells will eventually go to the most apical layer and will be gone. So, if you transplant the truly defined stem cells, then I don't think there's any danger of nefarious outcomes. The worst thing can happen is that you lose the graft because it will differentiate and give rise to normal tissue. But I don't think these things will be particularly problematic in our case. Also, dermal papilla, for example, this type of cells that do not proliferate in people. In fact, the minute we transplant them, they stop proliferation. And as Michael Randall showed very elegantly in his couple of recent papers, the first thing that happens to the dermal fibroblasts when they start aggregate and form prototype papilla cells is they stop proliferating. So that is definitely not an issue for the hair, that compartment. Epithelial stem cells, of course, do proliferate, and they have to proliferate. But again, if that's a true epithelial stem cells, they'll have to be maintained within a compartment with appropriate signaling. And that signaling ensures that these cells is not going out of its way and maintain the appropriate differentiation capacity. So, bottom line, providing we have enough controls, such as whole genome sequencing of the transplanting cells, and ensure that there's no nefarious mutations, your RAS and MYC and whatnot is not mutated, and there's no aberrant, consequences of proliferation of amplification in the dish. I don't think that's a problem.
Okay, well, that's good to know. One last question. I was with a number of people actually in Zurich at a conference in 2006, and they were talking about rolling out a clinically available version of cloning cells in the next year. We thought it was going to be ready to go in 2007, but here it is 13 years later, and we haven't heard as much about it. I don't want you to give anything away, but can you predict when we may have a clinically available or useful form of autologous cells to use to put in people's scalp, have them grow hair?
I won't promise you next year. That's not going to happen in the next year. But yeah, there's a challenges. There are challenges with the amplification of dermal papilla. In fact, anapithelial stem cells and adult cells from humans. And there's some beautiful discoveries in different branches of science with respect to how they could be managed. Michael DeLuca using 3D3 cells to amplify the epithelial cells from the skin, and they're using for transplants in the patients with different cutaneous diseases. Actually, can have the polyclone that will repopulate the entire surface of the skin, or a significant amount of the surface, saving the life-saving therapy. So, showing that this, in some occasions, you can see that you can have the epithelial stem cells being amplified to a large extent, and that's a property of epithelial cells. With the dermal papilla, things are more difficult, and I think until now, there's beautiful discoveries and investment, of course, with Angela Cristiano, and then Claire Higgins' paper published several years ago, where the three-dimensional aggregation of dermal papilla and providing specific factors help them to maintain the phenotype to some extent. Yet the maintenance of the dermal papilla on amplification, the adult cells, let alone indefinitely, but at least a significant degree, so you can repopulate a large number of hair follicles, I think is still a challenge. So with our technology, when you're talking about regeneration based on iPSCs, regenerative medicine, of course, we call it, the initial amplification of the material is not a problem. The iPSC can be made in buckets, and that's not a big deal. The differentiation of a particular cell type is more challenging. So I think we're very close to solve that differentiation challenge almost entirely. And so we're getting the cell types that quite resemble fetal, immature cell types in the human bodies. Now, the second challenge, of course, is to put them together and aggregate and make sure they talk to each other. And there's a challenge of transplanting them in appropriate form and shape. So they form these follicles, and then the follicles actually, the hair is capable to go all the way up and penetrate the skin. So there are a number of challenges to solve, but I want to think that these challenges are I want to call them like trivial, but I would think that they're more technical than fundamental. I think we solved the fundamental challenge of having the right cell type. There's still important challenges of properly aggregating them and enabling them to form the follicle. And I share some of this, our initial discoveries during the talk, but I think it will still take us a number of years to get to the point where we'll be able to, deploy the autologous hair follicles to the clinic. And I'm itching to give you the number, but I'll restrain myself from giving you the exact number. But I can tell that it's safe to say that it will take at least 3 to 4 years, and it's probably a little more than that before we actually can safely deploy. Because even if we know how to do it, we need to go through a large animal study. Mouse, unfortunately, is not a perfect model for human skin, as you know probably better than anybody else. The skin in the mouse is very different from humans. So the large animal models are critical here. And so, and then the clinical trials. So it's a long road.
Right.
But we're very confident and enthusiastic walking this road.
So you're not going to put us hair movers or hair transplanters out of business for a while. We can still keep moving the intact follicles.
I would never put you out of business. In fact, I'd love you guys to work with us, because I don't know how to transplant hair. I may be able to generate unlimited amount of hair for you to transplant.
But it still needs to be mechanically moved, huh? Put in the right place.
At this point. Unless, of course, restoration robotics will advance to the point that all of us will just need to push a button.
Yeah. So okay. Well, we have a couple questions. I don't know if we have time, but we can try. One is, do you think it will be an injectable treatment or an implantation treatment first? Injectable or something. Could you turn your volume down just a little? We're getting that static, a little bit of static.
I turned my volume almost entirely. How about this?
Yeah, it's just we're getting kind of a static on the line.
Are you still getting static?
Yeah, it was kind of like it was before. It went away, but then you were breaking up. But we can still understand you.
I can turn off the volume entirely when I'm talking.
Yeah.
So the question about implantation versus injection. So I think the solution that we're thinking about and we're investigating right now incorporate the scaffold. And so therefore, it's a transplantation rather than just injection of the cells. So it is a scaffold and the cells. We're thinking very actively of whether we can eliminate the scaffold and do something just with the cells. But that's probably the next step of the next iteration of the solution. The first one will be having the scaffold. Now, there's different types of the scaffold that we're thinking about, and there's many different ways to transplant it, including robotics. So we talked actually to the company, the automation company, who can maybe help us to visualize how this transplantation can be automated. Because, of course, once you get a limited number of these units to transplant, you may want to transplant 100,000, which is the number of hairs originally when we all born. And 100,000 units transplanting by hand might be a little kind of, tiresome. It can take some time.
Right. And we run out of time on that. Okay, well, Alexey, thank you very much for joining us, and please register for the conference. The conference starts on the 16th. You can hear Terskikh on October 18th at 10 a.m. Central Standard Time to hear his lecture on induced pluripotent stem cells into folliculogenic dermal papilla cells. We've kind of been dancing around that here, using a three-dimensional biodegradable scaffold. But to hear him, you're going to have to register, and you can register at 28annual.org. That's 28annual.org to register. A replay of this event will be available shortly, so please share it on social media using the hashtag #ISHRS 2020. Okay. Thank you again, Alexey, and we will see you on the 18th. I think even before that on some panels. So thank you so much for joining us. Okay, thanks again. We'll see you soon.